Section: Introduction. In this section, we discuss the significant role of large language models, LLMs, in various fields, particularly through prompting techniques like chain of thought, COT, prompting. This method encourages LLMs to break down complex problems into simpler steps, mimicking human reasoning. COT prompting has shown effectiveness in tasks that require logical thinking, math problem solving, and common sense reasoning. However, upon closer inspection, we find inconsistencies that challenge the idea that LLMs truly engage in logical reasoning. For example, when asked if the year the US was established was a leap year or a normal year, the LLM Gemini correctly identifies that 1776 is divisible by 4 and states it is a leap year, but then incorrectly concludes it is a normal year. This highlights a troubling pattern where LLMs can follow reasoning steps but still arrive at contradictory conclusions. Our analysis indicates that LLMs often rely on surface-level semantics rather than genuine logical processes. They tend to create superficial reasoning chains based on learned associations, struggling with tasks that require deeper understanding. Their performance declines significantly when irrelevant information is introduced, revealing their inability to grasp underlying logic. This issue becomes more pronounced with complex tasks, where LLMs frequently produce incoherent answers. Given these findings, we question the reliability of COT reasoning and propose examining it through the lens of data distribution. We hypothesize that COT reasoning reflects learned biases from training data, which limits its effectiveness based on how closely test queries match that data. We analyze COT reasoning across 3 dimensions. 1. Task, its ability to handle new task structures. 2. Length, its performance with different chain lengths. And 3. Format, its sensitivity to variations in query phrasing. To explore these aspects, we introduce DATAALCHEMY, a controlled experimental framework that allows us to train LLMs from scratch and systematically test them under various distribution shifts. Our findings indicate that COT reasoning performs well within distribution data but becomes fragile with even slight shifts. In some instances, LLMs produce fluent but logically inconsistent reasoning. These insights have important implications. For practitioners, they highlight the risks of treating COT as a straightforward solution for reasoning tasks and caution against equating its outputs with human reasoning. For researchers, they emphasize the ongoing challenge of achieving reasoning that is both accurate and generalizable, motivating the development of models that can move beyond mere pattern recognition. In summary, we present a novel perspective on COT reasoning through the data distribution lens, introduce a controlled environment for testing, validate our findings empirically across key dimensions, and underscore the real-world implications of our work for understanding LLM's reasoning capabilities. Section Summary. In this section, we explore the limitations of chain of thought, COT, reasoning in large language models, LLMs, revealing that while COT can produce structured outputs, it often relies on surface-level patterns rather than genuine logical inference, leading to inconsistencies. We introduce DATAALCHEMY, a controlled experimental framework to analyze COT reasoning under various distribution shifts, demonstrating that its effectiveness diminishes significantly when faced with tasks outside the training data distribution. Section: Related work. In this section, we discuss related work on prompting techniques for large language models, LLMs, particularly focusing on chain of thought, COT, prompting. COT prompting has transformed how we extract reasoning from LLMs by breaking down complex problems into smaller, manageable steps. By adding reasoning chains to few-shot examples, we have seen significant improvements in various tasks. Several adaptations of COT have emerged, such as zero-shot COT, which uses instructional prompts to trigger reasoning without examples, and self-consistency, which improves results through majority voting on sampled reasoning paths. To minimize manual effort, AutoCOT generates examples using the models themselves. We also explore tree of thought, TOT, which treats COT as a tree search over partial reasoning paths, allowing for look-ahead and backtracking. SymCoT merges symbolic reasoning with COT by converting problems into formal representations. Recent advancements have integrated COT into the LLM inference process, enabling flexible strategies like correcting mistakes and exploring alternative reasoning paths. While many view these prompting techniques as evidence of human-like reasoning in LLMs, we challenge this perspective by adopting a data-centric approach, showing that COT behavior largely results from pattern matching within training distributions. We then address the illusion of LLM reasoning. Although COT prompting has led to impressive results, research has raised concerns about the reliability of these improvements. Studies indicate that minor changes, like irrelevant phrases, can significantly impact performance, revealing that models often focus on superficial details rather than essential information. Additionally, models may produce longer but flawed reasoning paths that yield better answers than shorter, correct ones. We also note that performance does not always align with problem complexity, as models may struggle with easier problems and give up on harder ones. Intervention studies show that final answers can remain unchanged even when intermediate steps are incorrect, highlighting the illusion of transparency. These findings suggest that LLMs may not be true reasoners but rather advanced simulators of reasoning like text, and we still lack a systematic understanding of when and why COT reasoning fails. Next, we examine out-of-distribution, OOD, generalization, a significant challenge for LLMs. Research indicates that LLMs often revert to familiar functions when faced with new tasks. COT prompting has shown to enhance OOD generalization, particularly for multi-step problems, but this ability is not inherent to COT and relies heavily on model architecture and training setups. For example, strong generalization in arithmetic tasks was achieved only when algorithmic structures were encoded into positional encodings. We find that COT generalizes well when test inputs share structures with training data, but struggles with genuinely novel tasks. Given these insights, we propose rethinking COT reasoning through a data distribution lens, breaking it down into task, length, and format generalization, and systematically investigating each aspect. We suggest a fundamental reframing of COT, positing that it operates as a pattern matching process rather than executing explicit reasoning procedures. We believe COT's success arises from its ability to generalize to OOD test cases that resemble in distribution examples. We model COT prompting as a conditional generation process influenced by the training data's distributional properties. We define the training distribution over input-output pairs, where the model learns to approximate solutions by minimizing risk over training samples. At inference, the model generates responses based on patterns learned from the training data, and the degree of generalization is determined by the distributional difference between training and test data. We identify three critical dimensions of distributional shifts that reveal COT's pattern-matching nature: task generalization, which examines how well COT adapts to different reasoning tasks; length generalization, which assesses COT's robustness to varying lengths of reasoning chains; and format generalization, which explores COT's sensitivity to changes in prompt structure. By systematically varying these dimensions in controlled experiments, we aim to validate our hypothesis that COT performance declines predictably as distributional discrepancies increase, highlighting its fundamental nature as a pattern matching system rather than a true reasoning system. Section Summary. In this section, we explore the evolution and limitations of chain of thought, COT, prompting in large language models, LLMs, highlighting that while COT has improved reasoning tasks, its effectiveness largely stems from pattern matching within training distributions rather than true reasoning capabilities. We propose a data distribution perspective to analyze COT's performance across task, length, and format generalization, revealing that its success diminishes with increasing distributional discrepancies. Section: Data Alchemy, an isolated and controlled environment. In this section, we introduce DATAALCHEMY, a framework that allows us to systematically study how changes in data distribution affect the reasoning abilities of language models. This controlled environment lets us train these models from the ground up under specific conditions, enabling us to analyze their behavior in various out-of-distribution scenarios. We define a set of 26 basic atoms, represented by the letters A through Z. An element is an ordered sequence of these atoms, where the length of the sequence can vary. This design allows us to adjust the size of our dataset by changing the length of the elements, which helps us train models with different capacities and examine their ability to generalize based on text length. We also introduce transformations, which are operations that modify elements. We focus on two main types, the Rot transformation and the cyclic position shift. For the Rot transformation, we use a mapping that assigns each character a number based on its position in the alphabet. This transformation shifts each atom in the sequence forward by a specified number of positions. For example, if we take the element consisting of the letters A, P, L, and E and apply a shift of 13, we get the new sequence N, C, Y, and R. The cyclic position shift, on the other hand, changes the positions of the atoms in the sequence. For instance, if we take the same element and shift it by one position, we would rearrange it to E, A, P, and L. To model more complex reasoning, we define a compositional transformation, which is the repeated application of a series of these operations. We can create a sequence of transformations, and by applying them one after the other to an initial element, we can generate a new element. This approach allows us to build intricate transformation chains and analyze the reasoning steps involved in the process. Section Summary. In this section, we introduce DATAALCHEMY, a synthetic dataset framework that allows us to systematically study the effects of distributional shifts on chain of thought, COT, reasoning by training language models under controlled conditions. We define basic elements and transformations, including Rot and cyclic position shift, to manipulate dataset size and probe text length generalization, enabling complex transformation chains that facilitate multi-step reasoning analysis. Section: Environment Setting. In this section, we describe our environment setting. We utilize DATAALCHEMY, which allows us to systematically manipulate elements and transformations, creating a flexible framework for training large language models, LLMs, from scratch. This setup enables us to thoroughly investigate various out-of-distribution (OOD) scenarios. For our experiments, we use a decoder-only language model, specifically GPT-2, configured with 4 layers, 32 hidden dimensions, and 4 attention heads, along with a byte pair encoding (BPE) tokenizer. Both the LLMs and the tokenizer adhere to the standard modern LLM pipeline. During inference, we set the temperature to a very low value of 100,000th. We also explore LLMs with different parameters, architectures, and temperatures, as detailed in the appendix. We consider each element to consist of 4 basic atoms, resulting in 456,976 samples for each dataset with various transformations and token counts. We initialize 2 transformations, one that rotates text by 13 positions and another that shifts text by 1 position. We evaluate the performance using metrics such as exact match rate, Levenshtein distance, edit distance, and BLEU score, focusing on the reasoning steps, answers, and complete chains produced. Next, we address task generalization, which is a key challenge for chain of thought, COT, reasoning, as it tests the model's ability to apply learned concepts to new scenarios. We break down task generalization into 2 main aspects: element generalization and transformation generalization. We introduce a measure for generalization difficulty, termed task generalization complexity, which assesses the discrepancy in tasks based on the reasoning chain operating on elements. We define a threshold for task generalization failure, indicating that when the complexity exceeds this threshold, the likelihood of correct COT reasoning drops significantly. For transformation generalization, we evaluate how well COT reasoning can adapt to new transformations during testing, which is common in real-world applications. We conduct experiments by varying transformations between training and testing sets while keeping other factors constant. We categorize the distribution shifts in transformations into 4 levels: in distribution, ID; composition, CMP; partial out of distribution, POOD; and out of distribution, OOD. Our findings show that the effectiveness of COT reasoning generally declines as the distribution discrepancy increases. For instance, as we move from ID to CMP, POOD, and OOD, the exact match rate drops significantly, while the edit distance increases. In most cases, LLMs struggle to produce correct full chains outside of ID conditions, although they occasionally succeed under some CMP and POOD scenarios by chance. When we analyze the reasoning steps and answers separately, we find a strong correlation between them. In cases of composition generalization, the reasoning steps may be correct, but the answers can be wrong. This suggests that LLMs attempt to generalize reasoning paths based on the most similar transformations seen during training, leading to correct reasoning but incorrect answers. To further investigate when COT reasoning can generalize to unseen transformations, we perform supervised fine-tuning on a small portion of unseen data. Our results indicate that even a tiny amount of this data can help the model quickly adapt to new transformations, demonstrating that less discrepancy between training and testing data facilitates faster generalization. Section Summary. In this section, we present DATAALCHEMY, a framework for training LLMs like GPT-2, enabling the exploration of out-of-distribution, OOD, scenarios through systematic manipulation of elements and transformations. We analyze task generalization and its complexities, revealing that LLMs struggle to generalize to novel transformations, often relying on learned patterns rather than true understanding, while supervised fine-tuning on a small amount of unseen data can enhance their ability to generalize. Section: Element Generalization. In this section, we discuss element generalization, which is vital for large language models, LLMs, as they adapt to new tasks. We set up experiments similar to those for transformation generalization, focusing on three types of distribution shifts: in distribution, ID, composition, CMP, and out of distribution, OOD. In our tests, we examine if chain of thought, COT, reasoning can be applied to new combinations of basic elements, such as rearranging a set of items. The CMP can be further explored based on the order of these elements, while OOD involves elements that the model has never encountered during training. Our findings reveal that, like transformation generalization, performance drops significantly with distribution shifts. For all cases, the exact match rate falls from 1 to 0 as we move from ID to CMP and OOD. Notably, the blue score drops to 0 when we apply certain transformations. We observed that the models struggle to produce any responses when faced with new elements. We also investigated when COT reasoning can generalize to these novel elements through supervised fine-tuning, SFT, and the results are summarized in a figure. We evaluated performance based on exact matches across 3 scenarios, finding that performance improves quickly with similar training examples. However, the exact match rate for COT reasoning aligns with a lower performance limit when the element order changes significantly, suggesting limited generalization capabilities. When we analyzed the exact matches of reasoning, answers, and tokens during training, we found discrepancies in accuracy that might explain the inconsistencies in COT reasoning. Next, we explore length generalization, which looks at how COT reasoning performance declines when models encounter test cases of different lengths than those seen during training. We break this down into 2 parts: text length generalization and reasoning step generalization. We propose measuring the length discrepancy to understand this better. For length extrapolation, we establish a power law relationship indicating that the generalization error at a test length follows a Gaussian distribution based on the training length. In terms of text length generalization, we assess how COT performance changes with varying input text lengths. This is important because real-world problems often involve different complexities reflected in the length of problem statements. We pre-train LLMs on a dataset with a fixed text length and evaluate performance across various lengths, using different padding strategies. Our findings show that COT reasoning struggles to generate responses for test cases with mild length shifts. Performance declines as the length difference increases, with blue scores dropping significantly. We noticed that LLMs tend to adjust their reasoning lengths to match training data by adding or removing tokens. The effectiveness of length generalization decreases with greater discrepancies. We also tested different padding strategies and found that while padding to the maximum length did not help, using a grouping strategy improved performance, indicating its effectiveness. Section Summary. In this section, we explore element generalization and length generalization in LLMs, finding that performance significantly declines when faced with distribution shifts, particularly with novel elements or varying input lengths. Our experiments reveal that COT reasoning struggles to generalize effectively, with performance improving only when training examples closely match test cases, and that certain padding strategies can enhance length generalization. Section: Reasoning Step Generalization. In this section, we explore reasoning step generalization, which examines if models can extend their reasoning to different step counts than those seen during training. This is particularly relevant in multi-step reasoning tasks. For our experiments, we first pre-train the large language model, LLM, with 2 reasoning steps and then evaluate it on data requiring 1 or 3 steps. Our findings, illustrated in a figure, show that chain of thought, COT, reasoning struggles to generalize across different step requirements, indicating a failure in generalization. We then attempt to reduce the differences in data distribution by gradually increasing the amount of unseen data while keeping the dataset size constant during pre-training. We evaluate performance on 2 datasets and observe that as the ratio of unseen data increases, performance on the target dataset improves. However, the LLMs do not generalize well to the original training dataset due to limited training data. This trend aligns with our expectations and supports our hypothesis. Next, we assess format generalization, which tests how well COT reasoning adapts to surface-level changes in test queries. This aspect is crucial for understanding if models have developed flexible reasoning strategies or if they depend on specific training templates. We introduce a metric called the format alignment score to measure how similar prompts are. We simulate real-world scenarios using 4 perturbation modes: insertion, deletion, modification, and a hybrid mode that combines these changes. Each mode is applied with certain probabilities to measure the model's resilience to shifts in prompt distribution. Our findings reveal that COT reasoning is significantly affected by format changes, with deletions having a minor impact and insertions being more influential. We further analyze the query components and find that elements and transformations are critical to format, while changes to other tokens have little effect. We also investigate how variations in sampling temperature and model size affect the stability and robustness of COT reasoning. We examine different temperature settings and find that LLMs maintain consistent COT reasoning across a wide range of temperatures, as long as they stay within a suitable range. We then assess the impact of model size using the same experimental setup as in our previous studies. Our results show that models of different sizes yield similar accuracy across various settings. In our discussion, we conclude that the reasoning capabilities of COT are more fragile than they appear. Our experiments indicate that COT does not facilitate true logical inference but rather relies on structured pattern matching, limited by the training data distribution. When faced with even slight deviations from this distribution, performance drops significantly, revealing the superficial nature of the reasoning produced. Although our experiments used models trained from scratch, these insights apply to larger pre-trained models as well. We highlight several implications for practitioners. First, we should avoid over-reliance on COT as a reliable reasoning tool, especially in critical fields like medicine or finance, where misleading but plausible reasoning can be more harmful than outright errors. Second, standard validation methods are inadequate. We must implement rigorous out-of-distribution testing to uncover vulnerabilities. Lastly, while supervised fine-tuning can improve performance on specific data distributions, it should not be mistaken for true generalization, as it only slightly expands the model's effective range without addressing its fundamental reasoning limitations.